testing side channel security of cryptographic implementations against future microarchitectures. And the speakers are Chitchanok and Marco.
Okay. Good afternoon, everybody. Today I'm going to talk to you about how you can test whether your cryptographic implementation is secure against microarchitectural optimization from the future. Okay, so let's start. So computer architects and hardware vendors keep coming up with new and new fancy microarchitectural optimization, which is great because, you know, we go fast. But at the same time, we all know that microarchitectural optimizations come with side channels, which is not great in general. And in particularly, even more important, a recent study from Sanchez-Vicarta and others identified that a lot of optimization proposals that the computer architecture have been developing over the years, but are not implemented yet in modern CPUs, are actually security critical. They can be exploited to compromise our cryptographic implementations. And the core question that we're going to answer is, how can we evaluate the security impacts of these optimization proposals? And in particular, how we can do it, you know, early on, potentially before these implementations are implemented in silicon. And what I'm going to present next is a testing-based approach for reasoning about the security of cryptographic implementations for current and future microarchitectural proposals. So let's start with the very high-level pictures with a lot of gray boxes. I'm going to fill in the gray boxes throughout the presentation. So at a very high level, we start from a cryptographic implementation, potentially with some side channel mitigations implemented in it at software level, and a description of the optimization proposal that we want to test. And we're going to produce a list of potential problems indicating leaks. So let's try to refine this a bit. So the first step is, as I said before, we are talking about optimization from the future, so they might actually not be available yet in modern CPUs. So we're going to replace the description of the implementation of the optimization proposal with a leakage model, which is a formal model capturing at high level what information might be leaked through a side channel to a side channel attacker. And for everything that we need here, you can think of a leakage model as something that maps a program execution to a leakage trace, namely a sequence of high-level observations describing what might be visible to a side channel attacker. And and we're taking a program as input. So to capture these leakage models, we developed a modeling language called LM-Spec, which I'm going to describe next. So what the user has to provide is this formal leakage model described in terms of a set of prediction clauses and a set of leakage clauses. So what leakage clauses do is they describe what kind of information is visible to a side channel attacker. In practice, they describe what ends up on the leakage trace, and users can formalize these leakage clauses by associating them with a set of high-level events that might happen during program execution. In particular, we support leakage clauses associated with changes to the value of architectural registers, both reads and writes, memory loads and stores, computation of addresses, evaluation of sub-expressions, and changes to the control flow statement. And the leakage clauses will describe, based on these events, how we compute observations. So let me give you a few concrete examples. Let's start with something that we all know, the standard side channel model, the standard constant time model, sorry. So this is how we implement it in our language. We produce observation based on 3 events. So whenever a memory load happens, then we are exposing on the trace the address. And we do the same for memory stores. So again, we expose the address to capture leaks through the data cache. Whereas for changes to the control flow, we add to the trace the resulting value, okay, the next program counter in practice, which can be encoded like this. So as I was saying from the beginning, right, the idea here is we can reason about microarchitectural optimizations from the future. So let's look at something that is slightly more interesting, namely, oops, I forgot the thingy. So let's look at something more interesting, namely an optimization proposal called silent store suppression. So the core idea behind this proposal is there might be, you might actually have some stores that are to a certain extent useless in the sense that they're not gonna change the value of the architectural memory. And computer architects have been coming up with ways of detecting these useless stores early on and suppressing them at the beginning of the CPU pipeline to speed up computation. And we can model the leaks associated with and over approximate the leaks associated with this optimization in our language with the following clause. So we intercept store operations. Whenever a store operation happens, we check if the value of the store operation, if the value that we're writing is the same as the current value of the memory. So the store operation is what is called silent. And if that's the case, we simply record that on the leakage trace because this store might be suppressed, and this might result in timing leak. Okay, so the second part of our language allows us to talk about speculatively executed instruction. In particular, we have prediction clauses, which at the very high level capture which mispredicted paths need to be explored during the testing. And we support both control flow and data flow speculation for this. So I'm not going to go too much in the details here. I will just give you a concrete example, namely how we model branch speculation in our language. So we do so with the following clause. Again, we intercept, the event that we intercept is changes to the control flow. So whenever there is a change in the control flow during the execution of our test case, we check if the instruction causing the change is a conditional branch. And if that's the case, we are going to produce a prediction. So we're going to mispredict the value of the program counter to the wrong path, right? So if the condition is satisfied, we're going to take the else branch. If the condition is not satisfied, we're going to take the then branch. And this is high level how we describe it. And I'm going to explain next how we actually use this to do testing, but in a very high level, you can think of it as our leakage model. We just explored the mispredicted path based on this prediction for a fixed number of steps. Okay, so now we know how to model, how to specify these leakage models. What can we do with them? We developed a tool that can be used to test programs and detect leaks based on this leakage model. So the user has to provide the leakage model, the prediction and leakage clauses. And then our tool takes as input a binary program, an x86 program. And importantly, we also need a labeled interface that describes what are the inputs to this program, to our cryptographic implementation, and whether they're public or secret. And what the tool will do is we'll produce a set of violations, namely a set of leaks. So to detect these leaks, what we will do is we will search for pair of executions that are public equivalent, namely the public part of the inputs are the same, but result in different leakage traces for the model. Okay, so this indicates that there is a secret dependent flow of information from the inputs to the leakage traces, which is what the attacker can observe. So how do we do it? Well, we start by generating pairs of inputs that are public equivalent by generating first one random state and then mutating the secret part to obtain a public equivalent state. Then the core part of our approach is an executable semantics for our leakage models. We actually take the prediction and leakage clauses specified by the user, and we compile them down into a set of event hooks for the Unicorn CPU emulator. So the way this works is during the execution, the leakage clauses will be compiled down to these hooks that intercept events and compute leakage observations whenever the condition of the leakage clause is satisfied. Whereas for prediction clauses, whenever there is an event that satisfies the clause, what we will do is we take a checkpoint of the emulation state. We compute the predictions following the what is specified in the model. We update the state based on these predictions. We explore the mispredicted path for a fixed number of steps while collecting the observations produced by the leakage clauses. And at the end, we just discard the computation. We go back to the initial state and we restore the state that we saved at the beginning. Okay, so this allows us to enrich the architectural simulation with additional speculative paths. So we do this twice for the two inputs, and we simply compare the traces produced by the model. So if the traces are different, we detected the leak, which gets reported to the user with additional information about where the leak is located. And otherwise, we just go back, we continue testing by generating a new pair, and we keep running this loop until time expires. And I think that's it. And Chitchanok will go on with the case study.
Thank you, Marco. Wrong button. So before I continue with our case studies, I would like to recall our motivation. So Marco has already explained about our tool, and our motivation is that we would like to evaluate security impact on cryptographic implementations due to microarchitectural optimization. So we need to say what microarchitectural optimization that we consider. And in our work, in our evaluation, we consider 18 of them. And these are from 8 main classes of microarchitectural optimization. So the first one is constant time. Second, silent store and register file compression, computation simplification, operand packing, computational reuse, cache line compression, and prefetching. So all these 8 classes, and if we consider their variants as well, then we will get in total 18 microarchitecture optimizations. And this is what Marco referred to leakage clause. And aside from the leakage clause, we need to specify another thing, which is prediction clause. And in our evaluation, we consider 6 execution models. So the first one as a baseline, sequential, or no prediction at all, or no speculation at all. And the rest 5 would be about speculation, which are conditional branch, straight line speculation, store bypass speculation, and return address. And for the return address speculation, we actually model 2 of them. So in total, we have 6. And if we consider these all together, in total, in our work, we consider 108 leakage model. And to the best of our knowledge, when we submitted our paper, this was the largest leakage model to be implemented in a single tool or a single language. And we believe this is still the largest. And aside from leakage clause and prediction clause, of course, we need to specify implementation that we want to test. And as we said that we want to focus on cryptographic implementation, then of course we consider cryptographic primitive. Consider 8 of them, ranged from symmetric to public key cryptography. Other than that, all these cryptographic implementation, they are from 5 popular libraries, which are libsodium, libjade, libnetl, cryptlib, and Rust crypto. So in total, we consider 25 implementations in our evaluation. You might want to see the result. So here is the evaluation result. I know it is pretty small, and I do not expect you to read. What I would like you to see is the overall picture of our evaluation. So I can tell you that each line, these are 25 implementations, and we group them into 5 libraries. So that's the row. And in terms of columns, these are 8 classes of microarchitectural optimizations. So the main 8 ones, and then sub columns would be the variants for each of them. And what you can see here, you can see that there's red in every line. So from our analysis, all analyzed implementation leaked. So that's why in each line, you will see red somewhere. And if we look at memory safe languages, like Rust, for example, so I highlighted there. So that doesn't significantly mitigate the risk. There's still leak even in Rust implementation. And if we consider constant time programming, there's still leaks. So like in libsodium or in libjade, they not fully prevent the leak. And if we look a little bit further, and this I need to zoom in a little bit, we found that majority of the leak that actually comes without prediction or during sequential. So I zoom in a little bit that we consider 6 execution model, and there are 6 diamond shape. And if they all have the same result, we just group them into 1. And before the end of this presentation, I would like to give one example which is leak from constant time swap. And this is from lip sodium, which should be constant time. So if you look at the code, so I have to say that for this one, we have two variables, f and g, in like 5-element array, and we want to either swap or not swap, depending on the Boolean bit or condition bit, and this is secret. So because lip sodium, this implementation follow constant time programming. So as you can see, there's no branches, there's no secret dependent array index. But then the way to do that, so first, the secret bit B is extend to 64 bits in mass, and then F and G, they're XOR together, and then into X, and then X, and with the mass. And mass could be all 0 or 1, depending on the bit. And the last two steps, just XOR X with F and G, respectively. And well, the leak, of course, doesn't come from constant time, but then it comes from something else. So the first part is come from register file compression. Why? Because if mass is 0, then if you AND with 0, then the result will be 0. Then it compressed into 0 register. And that's not the end. Then there's another leak come from computation simplification. So if mass is 0, again, XOR with 0, then the value will not change. Then computation can be simplified because that computation doesn't do anything. So XOR can be simplified. And the last one is that if the value of F and G, if they remain unchanged, so if the value are not swapped, then the memory will not be modified. Then again, then silent store comes in. Then if you store the same value, then you don't need to store in the first place because you store the same value. So there's another leak from silent store. And to summarize our work, so first we introduce the language to express this leakage model. And then we have a testing framework, which is automatically detect for the leak. We just let it run and wait for the result. And another thing is that we did extensive evaluation. And we found that if these microarchitectural optimization were in place, then all of these implementation would leak. And I would encourage you to look at our paper, and there will be more detail over there. And with that, we are happy to take questions.
So we have a couple of minutes to take questions. All right, then I'll ask one. Do you intend for this tool in the future to propose some solutions? So like if it highlights code that's at risk, could it propose a replacement code that would not leak?
It can be done. I think for a few of the leakage models that we've been playing with, we have good ideas on how to rewrite leaky snippets. But then it's still something that at the moment is kind of manual, and you need to come up with a smart transformation for each of the leakage models.
I mean, I would like to add a little bit that for this tool, it should be for the vendor as well, or people who try to do optimization. So maybe they could test whether that will be like security impact on some implementations, like for a cryptographic implementation. So this is meant to be the tool for them, developers and vendors as well.
Okay, yeah. Fantastic, thanks. All right, 16 seconds, go for it.
And to what extent are vendors responsive to this, like hardware vendors? Will they not ship a new optimization because it causes leakages?
I mean, I think I've had a chat with folks at Intel, they kind of like having tools to play with. Then are they gonna use them, or are they gonna do something based on the results? It's unclear.
Yeah.
Okay, then let's thank both speakers again.